Dear ladies and gentlemen, first of all, I'd like to say thank you very much to have the opportunity to talk about smart safety at the Empolis Exchange Summit today. Smart safety is a concept we are driving within TÜV to enable safe and resilient operation of connected machines and collaborative robots and AGVs. The new machinery directive will focus much more on security and also the usage of machine learning. How can we utilize these potential new technologies? By keeping the same or even a better safety level maintained. Safety principles require an upgrade to incorporate context-sensitive mission-critical decisions for connected factory lines. The foundation has to be an open source digital twin ecosystem, and I like to introduce principles how we can upgrade safety for such a system. I like to focus my talk on 4 topics. Do we need a 4th pillar in the safety world? What we have learned in the direction of digitized safety compliance management. Then I like to introduce the principles of smart safety. I like to address a couple of use cases to show you what is the way how we apply it and what are the benefits, and I'd like to end my talk with a summary of smart safety. Safety and trust into the production is based on 3 pillars that we are utilizing now since many years. Requirement in organizations, the capability of people, we train people and we have certification for persons. Requirements for the development process. We certify process capabilities to ensure that the quality in our products is achieved that we need for safety applications. And we have the 3rd pillar, the requirements for the product. We certify and test also products and have these 3 basic topics. So from the regulatory requirements, we derive the major topics, and then we have the industry standards, we come down to the segment standards. And what we see at the end of the day, it's mainly safety documentation. But safety documentation, even if it is Excel or PDF or requirement management, at the end of the day, it's paper-based. And what I like to discuss today is how can we bring this kind of documentation in the digital world. 10 years after Industry 4.0 was introduced and invented, we still miss the adaptive and autonomous factory lines, which are able to handle changes of products, changes of supply chains, different qualification of workers. We don't see this. We are still waiting. The question is, why is smart factory hardly available? The focus on decision making was missing. The focus on upgrade of a safety architecture to enable decision making for mission critical applications was missing in the past. How could industrial automation works without trust, and especially trust into safety and security? So we have to make our homework, and I like on the slide to show upgrade the safety principles from a static world, paper-based, PDF-based, into a more dynamic one, context-driven decision. Smart manufacturing, as we see on the right side, is based on data analytics at runtime, optimization of processes, predictive services. Mostly all of our customers are working in this world. The technical safety lifecycle has to incorporate all relevant changes during production and all modification during maintenance and so on. We have to accept that a static assessment has to be combined with some dynamic elements to generate the level of safety and security we need for this ecosystem. We at TÜV working since more than 5 years to add a 4th pillar, to this technical safety lifecycle. We call it very often an event-triggered hazard and technology assessment and a validation of the measures required at runtime. This fourth pillar is the enabler for concepts like plug and produce, and also smart safety or a condition-based safety under consideration of the environment of the machine and the state of factory, recipe, people and machines is required. What do we learn within TÜV? That is a topic I like to focus on in the second chapter and which direction we are going in the safety world. I like to focus on a technical life cycle of a machine because smart factories are consisting out of a number of machines, tools, software apps, people, workers, and so on. Let's start with the typical design phase of the machinery manufacturer. We make the correct hazard and risk assessment on paper. We develop the machines according to the rules. We integrate the machines and we conform the compliance typical with an attestation of conformity, well known as the so-called CE conformant. Then we start to modify on a daily basis, assuming mostly all minor changes will have no impact on the safety concept defined years ago. This is true if we have a limited number of changes and if the people can really judge all of these changes. But in the end of the day, today we have to accept hundreds of minor changes in apps, in software, in configuration, in recipes. And the question is simply, do we have, let's call the right safety measures in place that we have designed and agreed on a couple of months or years ago? So it is clear we have to be able to prove within the digital twin world if the assumptions we made, I call it here this slide at T0, are still true. And if yes, we go on. And if not, at least we should document these changes and we should be informed. We started at TÜV in the Smart Factory KL with the thinking of doing a risk assessment at runtime, and it's a very complex area, and the community is working since more than 10 years on risk assessment and runtime, and you know from autonomous driving that's a complicated task. Today I like to discuss that we do not need to, let's call it, do a complete risk assessment. We have to bring the right topics, hazards into the digital world, and then we can solve the problem in a robust way. How do we do this within TÜV? I think we have created to develop a machinery compliance platform, I think 5 years ago, where we bring all information about robots, machines, assets into one platform. So we have the safety requirements, we have the standards, we have the hazards, we have the control measures that are required to build a machine. And if you later on add the inspection results, you have everything at one single point of truth. What a customer gets from, I think we have statistical data about the hazard pool. We can analyze them. We can derive, let's call weaknesses and strengths of different machine types, of hazards, of safety measures. We have a project dashboard. We have an overview for our customer. And we have intelligent checklists because we learn during assessments what kind of specific questions will help to identify all weaknesses. We are starting to integrate digital safety rules within our own database by analyzing continuously all the hazards and the safety relevant data. And we need first the data, and the safety data are very important. Let's investigate for a minute the typical safety compliance process we are using since years, quite successful. So how it looks like, I start with the MCOM1 where we have the asset information, a typical machine, turning machine, something, a robot. So this robot, this machine, let's call it, have some intrinsic hazards during the development process of the machine. We investigate all the hazards that are, let's call, important for the intended use case, for the assumed usage of the robot, of the machine. For all these hazards, we do an extensive risk assessment and we document this. The required risk reduction for the intended use case is selected, and the typical, let's call, way is Number one, change the design of the robot or the machine. Let's call any asset with less hazards is better. So a machine design with potential less hazards is much better than a lot of additional safety measures. This is one of the basic safety principles, keep it simple. Of course, we cannot all hazards, we cannot design out all hazards, so therefore we need control measures, we need safety measures in our own asset, in the neighborhood, in the building, and so on. We develop them, we release them during the integration phase or the release of the machine. And there's a third point, and I like to highlight this one. We have a residual risk. Not all hazards and not all cases can be, let's call, controlled. We know it. We describe this residual risk in the documentation, and we train the workers for this specific or special hazardous situation, how they have to behave. Now the question is, do we have all this information within the IoT world? Hazards and risk are only communicated if, let's call, the vendor is forced to. So risk assessment, hazard, safety measures, it's a part of what we call IP protected. It's a part of why you select this machine, because they have a special way to design it in a proper way. So this is very important, and I like to step now to the next level. I like to compare the safety assessment that I explained a minute ago, assessment and compliance process of the left side, asset, intended use case, assumed hazards and safety measures. We bring it in the database, and we have now a setup where 3 HUVs, 3 robots, and a couple of people can work together and can collaborate. We have on the other side, in mostly all production lines, let's call a production monitoring system, where there are rules, there are data, ERP systems, there are production rules, they're defined by the factory owner. And we have the information that there's a new HUV. I marked it here with green, it's a little bit larger. And I also marked the robots, they are increased in size. So different vendors, different functions. We have to upgrade the 2 robots. We do have all information, but we still have a border between automation and safety. Does this make sense? No. So the question is, how do we connect the dots that the safety decisions based on safety cases static can be combined with context-sensitive real-time data and maybe additional hazards that you would only see in this situation. I like to summarize at the end, let's call this safety process in an overview. So on the left side, we design a machine. We have an intended use case. We do a proper hazard analysis. We do FMEA and FTA fault tree analysis for this design. We do a test and validation as all the safety measures are accurate, and if we can detect the people, the hand, and all the things that are critical, and we describe it in a safety case. Based on the safety case, we can do certification of the machine, we do the CE conformity, and then we integrate the machine in the factory line, and it depends on if it's a complete or incomplete machine, we have the CE conformity achieved. Now the question for us is, let's call, if we run the operation, if we modify the robot arm slightly, if we have some different recipes, if we do some maintenance, we have diagnostic running there, and we have the monitoring system of our automation. Do we have a safety case with the context, with all the information as of today? No, we don't have. And what is missing? The dependencies between all information in paperwork, in standards and assumptions, and the usage that we are having now at this moment in time. So this was the introduction, what we have learned. And now I like to show that if we apply the same principles and we add the safety semantic and the knowledge graph, that we do exactly the same and we can handle runtime or real-time situations. Let's look on the same what I have explained in the last chapter. So we have the asset, we have the hazards, risk assessment, required risk reduction, safety goal, avoid collision, and then we go in the design process. We have a database. So we have in our database the type of the machine and the hazard linked to the safety goals and the safety measures. We have enough statistics and we can do data analysis. Let's move now to an assessment during runtime. Why do we need an assessment during runtime? We like to increase the productivity. So preventing to run into this safety stop situation, what all of you know, yellow blinking machines that stopped due to any reason. Less downtime means higher production. What can we do if we are, let's call, doing assessment at runtime? We can change the route of the green HUV, so avoid the collision hazard. We cannot redesign the HUV or a machine. And if we cannot avoid the hazard, we can give a warning about at runtime about the residual risk using the green HUV compared to the blue one. If it is higher, if it is different, we have to inform the worker, the red dots in this slide. What is necessary? We need a way to communicate between different HUVs, between different people, between different robots. So that's what I like to show here. A colleague of me invented this, that we need a couple of layers to communicate in this factory line at runtime or even at real time, because we are discussing safety critical, mission critical operations. We started to fill the safety profile and we realized it is not enough to make decisions based on profiles. So therefore we created 4 layers of an information hierarchy that we would need to make a mission critical decision. Safety cannot be negotiated, and I cannot use data learning algorithm to make a safety decision. There are rules behind, and therefore we have a trust vector indicated. And I like to show briefly that we have to start with an identifier. So we have to classify our machines into groups linked by hazards. You see it here, actuator powered machine active as an example. If we have this 2 or 3 of them, then we start a communication, and at the first line we have to understand what is the trustworthiness of this other asset in terms of reliability, resilience, safety, security, and privacy. We are working in a digital twin consortium to, let's call, drive this concept of a digital twin trust vector in the communication layer if we target mission critical decisions. Then of course we need a digital twin safety profile. The safety profile is linked to the source of hazard and to the safety goal. And with these 3 basic layers, we can make a decision. If we like to go deeper because the other asset have the right trust level, we come to the measures, control measures, other measures that are developed and documented. And normally we have most of this information either on our side in MCOM1 or Industry 4.0, OPCUA, information models, administration cell, and so on. So again, the target that we have is change the route of the HUV, avoid the collision hazard if we expect a collision hazard, or warning at runtime about the residual risk, what could be, let's call, the critical part if the green HUV runs into the situation. I like to summarize again. What do we have changed now? We have the same hazard and control measures. We added a safety semantic. I would call it the digitized rules, how we make an assessment. We skip completely the risk assessment because we have enough data, let's call, for every situation to apply the right performance level. And now the question is, how do we compare the green HUV and all the information about the green one with the blue one, accepting that the world is incomplete. We are on a real factory line. Not all the fields are filled out as we would expect, and in the theoretical research level we always see. We replace the blue one by a green one, and using a knowledge graph, we have a knowledge graph for the blue one and we have a knowledge graph for the green one. And if we compare both of them, we see dependencies, and we see the important dependencies and based on this knowledge, we can make a decision. I like to briefly show my colleague Michael Pfeiffer has used an AGV left side theoretical one. We have the safety profile, prevent collision. You see a couple of brackets and information there, different layers. And on the right side, you see the same AGV now running in operation. What is difference? Now we have a load. So we know what is the weight of the things that we have loaded. We have the drive, we know the speed. And now we see a collision in front of us and we see the real hazard, and we compare the left side with the right side, and we can make some conclusions, what to do, what next. To get an understanding what we are meaning with a knowledge graph, making a connection between different kinds of information. There's a residual risk described in a standard. There's an assumption in the risk assessment on paperwork, and there's a situation that we see now and we can calculate if it fits to the left or the right side. This was in a nutshell, in 10 minutes, all about smart safety. I like to come to the use cases, and I like to start about smart safety. Productivity requires trustworthiness. And I like to say thanks to the Smart Factory in Kaiserslautern, to Professor Sülke that introduced me there, and to Professor Rutkowski that is driving the activities. All the things that I described in the last 20 minutes were developed together in different working groups within the Smart Factory, infrastructure or safety working groups over the last 5 years. And I copied in some sketch and some white papers so you can read. But the message today is I have to motivate the industry. It's time to step out of the research and to integrate these concepts in our factory lines to get more productivity and to come closer to the autonomous, let's call it, digital twin usage that we all need. The technology, digital twins, knowledge graphs give us the opportunity step by step to enable a more holistic understanding of our factory. So I have described it here. What is the awareness of the behavior and the environment? We don't discuss the theoretical intended use case. We discuss the condition that we have now. What is the temperature? If it is raining, if we are outside or not. What next? Trustworthiness in perception. What do we plan? What is the next operation? Do the next operation will bring us in a hazardous situation? Do we have to follow this planned assumption or not? And achieve how to achieve availability and safety, how we can combine, how we can balance the highest productivity with the highest safety requirements. And you see it now here. If I look on at T1, at this point in time, we have the weight of the workpiece, and we can, let's call it, calculate what is the probability that parts could fly away. We could stop still the operation because there is some time before the parts flying away. Safety lifecycle based on digital twin and knowledge graphs, that is the key message that I like to give. And what we learned to work together with using the Ampulis knowledge graph in the Smart Factory KL is we have to differentiate between two classes. One is the discussion about system level, will be described in the new Smart Factory KL white paper. And another one is the machine level, the asset internal interdependencies, what I try to describe in this presentation. And if we bring both worlds together, then we can utilize this and have excellent results. And now I like to show one or two complicated examples that you understand what is the capability. And I like to use a very simple turning machine. I skipped the pictures where some people get killed. So there's a turning machine, there's a workpiece, there's a protective door on every turning machine, and they can hold back, let's call a workpiece of 50 kilograms. If I now try to operate with a workpiece of 300 kilograms, of course, there is a residual risk that this part could fly away. I'm still allowed to work because the turning machine can handle maybe 350 kilogram workpieces. So what can we now address with smart safety? You would ask, you see the turning machine in every factory line. If we bring the workpiece, the turning machine, and the people together, what I'm doing on the next slide, we have a context-sensitive safety. If you realize that in front of the turning machine is a green worker, trust level safety 3, her operator is aware of residual risk, he is trained, he can decide by himself how to go on. If it is this yellow-green one, we have to inform the operator, are you aware that you have a residual risk now at this moment in time? Please step 50 centimeters to the left side and you are out of the risky area. If there are humans coming from a different company, we can communicate, we can give him the clear message, step to the left side and give him a warning there could be parts flying away. And if it is, let's call somebody that we cannot communicate with, lowest level on our trust spectrum, of course, we stop the operation. We inform the operator that he should take care that this guy disappears. So we bring now machine people together, and that's what it's all about in Industry 4.0. It's not only, let's call operate more, let's call to context sensitive decision. It's the target that we have in front of us. I like to summarize the basic summary. Safety will stay application specific. There are hundreds of standards. Hazards are, let's call, linked to safety integrity level by the risk assessment. We know this and we keep it everything what was developed in the past. But smart safety, domain and factory specific maturity model for the factory line will give us 3 options. If 90% of the information are available and the trustworthiness is given, we have context-sensitive decision, we optimize productivity. If only a limited number of information is given, but the trustworthiness of the assets is high, we can think about a degraded operation. Z4EE is discussing this in their standardization. And for me, the most important part, if we have significant risk because the intended use case does not cover the application, we have solved our liability problem. We document it and we know with the right safety experts what to do. At the end, I like to summarize what is smart safety. It's the process and the technology that we need to integrate or bring on top for a resilient production. So we need safety profiles. We need the same for security. I do not discuss in this keynote. We need semantic interoperability. I covered slightly semantic, and of course we have to start to collect data about hazards, about the control measures that I explained in the middle part of my presentation. We translated into Süd our word, let's call components and systems standalone, connected, dynamic, and smart, and we brought it together with the trustworthiness discussion of the IIC, privacy, safety, security, resilience. And we came to a simple example to say we need more resilience on the asset level and we need more resilience on the system level. And what does it mean? Utilize all the information that we have, because resilience means we have more information about the same topic as we need. If we collect all of them, we can make the decision that gives us the productivity. So this is the picture that shows, let's call, bring assets and hazards together, combine it with the knowledge graph, and you are able to increase the productivity. I like to end with what are the next steps to upgrade safety for connected machines. We need customized maturity models per factory line. We have to work on digitized safety and security compliance management to ensure higher productivity. So we have to design the machine and the system in a way that we can utilize this benefit. Süd is working on context-sensitive understanding, the decision-making for mission-critical application, handling of dependencies between assets at runtime, what do we need to make the decision, and to try to digitize together with our partners the rules to handle the gap. And that's what we are focusing. We are focusing only on the gap between the intended use case that we have designed for and the real use case. And if there is no gap expected, then we continue with the safety solutions we have. So the industrial community has to enable the tools and the infrastructure and the semantic that we can connect the required information at runtime. Thank you very much for your attention. And for questions, you can meet me right after this session in the breakout session to discuss all the topics that are of interest. I like to end with, let's call it this picture, and you can read it. It's in German. Methoden mag es eine Million geben oder noch mehr, aber Prinzipien gibt es nur wenige. Wer Prinzipien begreift, kann mit Erfolg seine eigenen Methoden auswählen. Wer Methoden ausprobiert und Prinzipien ignoriert, wird ohne Zweifel Probleme bekommen. So it's all about safety principles, situation awareness, and context-sensitive understanding why something has to be done. Thank you very much for your attention.